All right, let's go ahead and get started. We're starting with section 2.2 now. I put an announcement on Canvas last night that I'm going to have a review session on Tuesday night, the night before the test. That'll be on Zoom. So if you can make it, I would definitely encourage it. Also want to remind you that the MCC right down the hall in room 203 is open. I'm in there every Thursday and Friday afternoon, but if you need help with, anybody who is working there can help you with Calc 1. So if you need help with something, it's another great place along with the tutoring centers, both in this building and Hayden Library and all the other places where they are. Just another really good resource to keep in mind if and when you need help. Any questions about anything before we get started? All right, so last section we talked a lot about what a derivative is, what it means, how to find them. Now we're gonna go a little deeper. Pretty much everything we talked about for section 1 was finding a derivative at a point, even if that point was arbitrary. So now we're gonna expand that into this idea that the derivative is actually a function to itself, which is something I know we mentioned, but now we're gonna talk more about that. So if I have a function f, the derivative of f is given by this, which hopefully looks very familiar. It's just that now instead of me defining this derivative at some point x equals a, this new function f prime of x is a function that's based on f of x in this specific way. This function f prime exists whenever that limit exists. Or whenever f is, what's the word? If that limit exists, what can we say about the function f? It's differentiable. It's differentiable.
What is differentiable?
What's that?
What's differentiability again?
Well, you literally just said it. So I'll write that down before I talk more about that. So the definition of this word differentiable in this context is that if a function f is differentiable, let's just say if it's differentiable at a point, then this limit exists. That is the most literal foundational definition of that word differentiable. Now I word it this way not to trivialize it, but it really is what this word means. If a function is differentiable, its derivative exists. So, which is not always the case. We'll talk about today. I think I've used a lot of different notation for derivatives, but let's just go ahead and let's talk about it explicitly. So typically you've probably thought about this for years now that f of x is another way to express a y value. If I have a function called f, I can feed some input value x to this function, and the function will deliver some output value y. So most of our derivative notations are based on that function notation. So we've talked about f prime of x. F prime of x is that function is the derivative of f. We also call it y prime, dy dx, df of x, dx. But pretty much everything on that second bullet there, those are all equal because they all say literally the same thing. Y is a function of x, and I'm going to differentiate y, or take the derivative of y with respect to x. And all of those names mean exactly the same thing. And you're going to see derivatives written in a lot of different ways. And I am by no means saying this is a complete list. The one on the bottom there is a little bit different because, so basically everything on that second bullet, that's me treating the derivative as a function. And that bottom bullet, that's me talking about the derivative at one particular location. So we'll get more practice with all those as we see them, they'll just pop up organically. But any question, anything up there that we haven't seen yet? I've tried to pepper a lot of those in. Go ahead.
What's that vertical line?
So this vertical line right here, this pipe.
Yeah.
What that means in this notation is, so dy dx is a function, right? this means restricted to. So dy dx is a function, but I want to restrict it to where x equals there. Which is hopefully you see that's consistent with this. I don't really care about this derivative at any place that's not x equals there. Anything else before we go on? Okay. So now that we have that, I have this function here. Now I can just find df dx. Instead of finding its derivative at some point, I can find its derivative at all points. One thing I want to ask before we do that though is what's the domain of f?
-2.
So we have -2 to infinity. Do I include -2?
Yes.
You okay with why we include -2? And so yeah, the square root of 0 is a well-defined thing. So I agree with that domain. So now let's do this. Let's find the derivative here. So df dx equals, I'm sorry, was there?
Yeah, so the D just, it's like the derivative.
So I'll word it a different way here. So if you see this operator right here, ddx, that ddx right there means I'm going to take the derivative of whatever is about to follow. So I can write ddx of f of x. But it's kind of like, I'll give you a kind of a silly example. If I wrote that, what does that mean to you? It's a square root symbol, right? Does that mean anything without me taking the square root of something? So that's kind of like ddx. ddx by itself is meaningless because it's ddx means I'm going to take the derivative of whatever you have attached me to. So, and this is probably, I don't know if this was on that slide, but ddx of f, so the derivative of f of x, that's another way for me to represent df dx or f prime of x. Like maybe little historical insight. Calculus was something that was basically discovered and developed by two different people at the exact same time in different locations. So the ideas were all kind of the same, but the way they represented them were all wildly different, and we kind of inherited both, which is why you see these different looking notations meaning the same ideas. So I want to find a derivative so I can, all derivatives come from the same place, this limit. So the limit as h approaches 0 of the square root of x plus h plus 2 minus the square root of x plus 2 all over h. So not a limit I can evaluate yet, but is there a way I can start working up to that? What's a good way that I can manipulate this?
That conjugate, right?
What tells you conjugate here?
Square root.
Square roots, right? And that's one of the most common things, especially when you're dealing with real numbers. Most common thing conjugates are used for. So multiply by radical x plus h plus 2 plus radical x plus 2. So after I do this, what is my denominator, or what's my numerator going to end up looking like?
Same thing, just draw the square root.
So pretty much the same thing without square roots. Here's my only caution to throw at you, and I'm going to go ahead and make an intentional error. So x plus h plus 2 minus x plus 2 all over h. Oh, not all over h. Can't lose that conjugate. All right, are we okay with what I have here?
No,
No, what did I do wrong?
you need to put parentheses after.
Right, and the reason I missed that is because I'm willing to bet that at least one of you didn't notice that I dropped that. So yeah, keep in mind this x plus 2 here it's pretty obvious that these things are connected by addition when they're in the square root. It becomes a little less obvious when the square root gets cleared. But that absolutely is the case.
So there doesn't need to be parentheses around the first three.
I mean, I could do this, but,
Just wouldn't matter if it's not.
and because
There's no operation.
when you're subtracting two things, it's only the second. It's only the seconds of those two terms that. That's the right way to say it. The order matters, right?
Yeah, I'm just making sure.
So. Before I made this change, I was only subtracting x. I really need to subtract x and 2. So because of that, what's going to happen? Right, so we've done a few of these, let's go ahead and fast forward a couple steps here. X and x cancel, 2 and 2 cancel. But also now I'm going to have h over h, right? So I can hopefully do this 1 over the square root of, I don't need that much square root, the square root of x plus h plus 2. Plus the square root of x plus 2. Can that be evaluated? Can that limit be evaluated? Should we find out? So as h goes to 0, I have 1 over radical x plus 2 plus radical x plus 2, right? Go ahead.
You plug in the zeros and it becomes x plus 2 or square root x plus 2 plus square root x plus 2.
Yep.
And 1 over 2 root x plus 2.
Right. So yeah, I'll go ahead and
The H's cancel out too, right?
the what?
The H's cancel out too, like the step before.
Yes. Yeah. So the x and the 2 cancel through subtraction and the h's cancel through division. So yeah, what I have is 1 over 2 times the radical x plus 2. So that is our derivative. Does it have the same domain as the function, as the original function?
Yeah.
See, I saw some head shakes and I heard some yeses. One of those is right. What do we think?
It didn't have, no, if square root of 0 is 0.
Right, so -2 is not the domain of the derivative, right? So yes, the square root of 0 is defined, but 1 divided by 0 is not. So did this to highlight that they don't always share the same domain. So the domain of f was, yeah, the domain of f prime is exclusively -2. Any questions about how we found this derivative? Why we're saying the things we are about the domains? Would it make sense for the derivative to have a bigger domain than the function itself? Not really. I mean, if the function is not defined, then can't really talk about what the rate of change of the function is in places where it doesn't exist. All right, how about this function? What is this function again? It's the absolute value of x. So I want to know where that thing is differentiable. So let's do a couple different things here. This graph sort of looks like this. And let's do this. Another way to define this function, which I may have shown you. If I haven't, we'll do it now. So what does an absolute value do? Go ahead. Makes everything positive, right? Or at the very least non-negative. So if I give the absolute value function a positive number, what does the function give me? It gives me the same number, right? So this function equals x if x is at least 0. If I give it a negative number, what does the function give me back? Gives me a positive number, right? So if I give it -2, it'll give me, if I give it -1, it'll give me 1. So basically, this function gives me -x if x is less than 0. Go ahead and stop there. Any questions about, are we okay with that definition? I mean, we already understand, and I think hopefully we understand that if the absolute value only gives back non-negative outputs, and these two branches right here are guaranteed to give you non-negative outputs. All right, so I want to know if this function is differentiable. So we've talked about derivative as a slope of the tangent line, right? So because of that, I'm gonna ask if we can say, all right, if we have numbers that are strictly positive, that function should be differentiable, right? Because everything on the right of the y-axis, you just have a straight line. Everything on the left of the y-axis, you have a straight line. So the only real problem is what happens at x equals 0. So let's see if we can figure that out. So let's look at the limit. And really, I want to look at the limit as around the point x equals 0. So I'm going to do this, the limit as all right, does this limit exist? This is what f prime of 0 would be if it existed. What's that?
Is that just f of h over h?
F of h minus, 0 over h, right?
Yeah.
So the limit as h approaches 0 of f of h over h. All right, so we've made it look a lot simpler. Does this limit exist?
No, because if you put 0 in the nine, whatever, just on all.
Right, that's okay, because I don't want h to become 0, I want h to get near it. So that doesn't mean, you're right, it's not defined as 0, at h equals 0, but
Also, the limit doesn't-
might be okay. No, I'm not saying the limit does exist, I'm saying that the Solomon's condition is not enough to break. So this is a two-sided limit, right?
Yeah.
These are pretty hard to think about, sometimes all at once, so if we can isolate this into, let's just break it up into positive and negative. What's the limit of, what is f of h as h approaches 0 from the right? Another way to say this is, so it's going to get closer and closer to 0, right? But what is f of h
Whatever.
for any value of h as I go to 0 from the right?
Same as that, just.
It's just h, right? I mean, that's kind of why I did this piecewise definition up here.
I mean,
So if I'm restricting h to only positive values of h, if I'm restricting h to only being positive, then I can say that f of h is equal to h, right? So this becomes h over h, which is 1. So we have the right-hand limit exists, right? But what if we look at the left-hand limit? We're looking at the same limit, f of h over h. What will f of h be in this case?
no, so h,
It's not still h.
what's negative 10?
So f of h, so for this one here, I want h to approach 0, but it's going to be negative all the time, right?
Positive.
Well, I mean, the input itself will be negative,
Negative.
which means the output is going to be, is going to be defined by that top branch. So in this case, I have this limit is negative h over h, which is negative 1. What does that say about the limit? Doesn't exist, right? So this function is differentiable for all x values that are not zero. So before I take some questions on that, let's talk about this in terms of graphs a little bit more. Are we okay with the idea that, graphically speaking, the derivative is the slope of the tangent line? What's the slope of this function anywhere on the right-hand side of the y-axis? It's 1, right?
Yeah.
So I have this, pretend it's a horizontal line, be just a straight line of 1, right? What's the slope of the tangent line anywhere to the left of the y-axis? -1. So the derivative is not continuous at x equals 0, right? So that's another way to look at it. Here's another way. A tangent line at some curve is just, there's 1, right? There's only one place where the slope makes sense. Another way to do a tangent line is it's a line that touches the curve at one place, right? Is there one line you could draw that would be tangent to that, to the origin of that curve? I mean, I think I could do it in lots of different ways. The x-axis is tangent to that, but I really have a lot of freedom, right? I don't have a unique tangent line I can draw, which means the limit can't exist. There's only, remember, for the limit to exist, how many limits can there be?
If it exists.
If there exists one, so at most one. So the fact that I could draw, infinite number of tangent lines there is a problem.
Does a tangent line always have to be linear?
Yeah, it's a line. Any other questions here? All right, so yeah, this function is differentiable everywhere except for that cusp at x equals 0. So differentiability and continuity. So if I have as a function a is a real number, these two things are always true. If f is differentiable at a, then it must be continuous at a. And these two things are equivalent, but another way to interpret it is if f is not continuous at a, then f is not differentiable at a. So now we've talked about what it means for a function to be continuous. Differentiability is, it requires continuity and more. Any questions on that? Man, it's probably a little hard to get your head around unless we look at an example or two. But I think the big thing to kind of gravitate to right here is that differentiability requires everything that continuity requires, but also there's that other limit, the one that defines the derivative that also has to exist. And I don't know why I didn't realize this, but if we look back at our absolute value function, is the absolute value function continuous at x equals 0? So the V looking thing, that's the graph of absolute value, right? As x approaches 0 from the left, what does the function approach? How about from the right? That function is continuous at x equals 0. But obviously, when we build this work to find it, it's not differentiable. So there are lots of functions that are continuous at a point, but not differentiable. So how about this one? I want to know, where is this function, this piecewise function, differentiable? So if I want to know where it's differentiable, what do I need to look at? What do I need to figure out? What does it mean for a function to be differentiable? The derivative has to exist, right? So I'm going to tell you right now, we've said that, a polynomial continuous everywhere. I'll tell you right now, the polynomial is also differentiable everywhere. So the reason I bring that up is, if you're less than 1, you're going to be differentiable. If you're greater than 1, you're going to be differentiable. So the only possible issue here is going to be that breakpoint where x equals 1. So I already know that all x values are differentiable except for 1. We got to look at 1.
So both polynomials and linear functions are differentiable everywhere.
You said polynomials and linear functions?
Yeah, polynomial.
Yeah, linear functions are polynomials. They're a specific type of polynomial. They're a simple type, but yeah, they are. So I'm looking for f prime of 1, which means I'm looking at this limit. The limit as h approaches 0 of f of 1 plus h minus f of 1 all over h. What's the problem with trying to look at this limit though, the way I've written it? H could be negative, right? It could be positive. And depending on what side of 1 I'm on, that's going to really change how that function looks. So I really should look at both these limits one at a time. So from the right, f of 1 plus h minus f of 1 all over h. If h is a positive number, what is f of 1 plus h? Which one of those two branches for this function applies when h is positive? X squared, right? Because f of 1 plus h, so x is bigger than 1, which falls into the bottom branch. So this becomes 1 plus h squared minus f of 1, which, what is f of 1? 1 squared, 1. So if you can't evaluate this limit yet, we'll go a little further. The limit as h approaches 0 of 1 plus 2h plus h squared minus 1 over h. So what ends up canceling there? The 1s, and then I can cancel an h in the numerator from both those terms with the 1 in the denominator, so I get the limit as h approaches 0 of 2 plus h, which is 2. So we got the limit from the right-hand side. Can we get the limit from the left-hand side? F of 1 plus h minus f of 1. Now, what is f of 1 plus h? Okay. 2x plus 7, so 2 times 1 plus h plus 7 minus f of 1, which is remember, we're talking about limits. So what function do I need to evaluate at 1 here? If h, remember, so h is approaching 0, right? But it's never going to be 0, go ahead. Oh yeah, it'll still be 1. I'm sorry, I got confused with something. Yeah, because f of 1 is 1, right?
Yeah.
All over h. I got that limit operator again. So I get 2 plus 2h plus 6. All over h. Simplify it one more time, but I'll tell you right now this limit doesn't exist. Eight over h plus 2. So I got the limit on the limit from the right exists, the limit from the left does not. So what does that mean about the limit?
That doesn't exist.
Doesn't exist, right? So is this differentiable at x equals 0? No. So this limit does not exist. So where is this differentiable? Everywhere where x is not equal to 1. So that was a lot of work to figure out that it's not differentiable at 1, right? We could have actually done something a little simpler, but I'm glad we didn't just jump to that. Is this continuous at x equals 1? So let's do this. What's f of 1? You said 1, right? What's the limit as x approaches 1 from the right of f of x? 2, right? No, it should be 2. How'd you get 2? That was the derivative, not the function. Should be 1, right? Because if x is bigger than 1, I'm going to use that bottom branch. So that's 1 squared equals 1. What if I come from the left? I'm going to use that other branch, right? So the limit as x approaches 1 from the left is going to be 2 times 1 plus 7, which is 9. So does that, do we have continuity at x equals 1? If we don't have continuity, what does that mean about differentiability? Yeah, it can't be. So remember, differentiability requires continuity and then some. So continuity could have solved that for us earlier. Any questions about that?
So if it's not continuous, there's no way it's differentiable.
Right.
But it can be continuous and not differentiable.
Right. Think about your absolute value function. That's continuous everywhere, but it's differentiable everywhere except for 1 point. How about this guy? Let's look at the graph. This is the cube root of x. Where is this thing differentiable? Let's start small. Give me an x value where it is differentiable. 1. Yeah, sure. X equals 1. If I could, I mean, let's talk in the language of graphs. If I'm looking at x equals 1, I could draw a tangent line. There's really no way for me to justify a tangent line in any other way. I'm going to make one tangent line there. It's unique. The derivative exists at x equals 1.
Not existent. X equals 0.
Does it not exist at x equals 0? Let's talk about that. Why would it not exist?
Because it's going kind of like that logic how we went from like increasing to decreasing the
Yeah.
same way. It's going like from left to right. It changes paths in the middle right there at 0.
Right, so well, it's increasing at a higher rate, increasing at a higher rate. What's gonna happen is I get to x equals 0. It's gonna be a vertical line, right? So if I have a vertical tangent line, which is what happens around here, what is the slope of that tangent line? Or 0 or undefined? How do you calculate slope in general? Like, or what does the word mean? Rise over run, so change in y over change in x, right? If I have a vertical line, what's the change in y?
Oh yeah, it's gonna be x and above.
Yeah, so there's no change in x, and I can have any amount of change in y, right? So because of that, I have a tangent line there with a slope of, couldn't tell you,
So it's
an undefined slope. So this is differentiable everywhere except for x equals 0. And that's a real, based on the tools that we have now, that's a really hard derivative to calculate. By the end of Monday, we'll be able to do it in literally 2 minutes. So keep an eye out for that. And when we do, I'll show you, it'll be even more clear why that derivative can't exist at x equals 0. But right now, hopefully the graph gives you some idea. Any other questions on this guy? All right. We've talked about, everything derivative we've talked about so far has just been, I don't think I've used this language yet, but it's been a first derivative. You can also just keep taking derivatives. Those are called higher order derivatives. So now I'm saying, I've talked about functions being differentiable. Now we're going to talk about functions that are infinitely differentiable, which means I can take the derivative of that function, and then I can take the derivative of that derivative, and then I can just continue that chain indefinitely. So those kinds of functions are infinitely differentiable. Polynomials fall in that category. So we've talked about f prime being the derivative of f. Now we're going to be specific and say f prime is the first derivative of f. And the reason we have to be specific about that is because we can go beyond that. F double prime is the second derivative of f. And based on the way I'm defining these things and the way I'm using one function to find other derivatives, f double prime is also how is f double prime related to f prime?
You have to take out time to get that.
You have to take, well, so how do you get f prime?
By doing the first derivative of f.
Right, so how do I, so now I have f and f prime, right? So now how do I get f double prime?
The derivative of prime.
I gotta take the derivative of f prime. So another way to think of this is f double prime is also the first derivative of f prime. And yes, we're in these, sometimes you have to look beyond one derivative, one order of derivatives. In general, the nth derivative of f, I actually don't even know how to read f to the n because it's not really f to the n, because it's not a power. But if that symbol right there is the nth derivative of f, then that is also the first derivative of what other thing? Not f prime. F, the n minus 1 derivative. And the reason I keep harping back on this first derivative thing is because if you have f, you can't just take the second derivative of it. You need to, that needs to happen sequentially. Those of you who are in engineering, especially the mechanical civil side of things, you will look at second and third derivatives. I don't know if there's, I don't know if it makes sense to go beyond that, but yeah, higher order derivatives are definitely worth looking at, important to look at. Any questions just about the terminology and how these things are related to each other? So let's find some. I have f of t equals t cubed. I want to find f triple prime of t. That's a polynomial, so I'm telling you it's derivative, it's differentiable everywhere. So if I want to find f triple prime of t, what do I have to do first? I gotta find derivative. So what can I call that first function I'm going to find? F prime t. So f prime of t is equal to the limit as h approaches 0 of f of t plus h minus f of t all over h. So f of t plus h is going to be t plus h cubed minus t cubed all over h. What happens when if you squaring them is kind of easy, what happens when I cube it? Do you remember? Do you feel like doing it? T cubed plus 3 t squared h plus 3 or t h squared plus h cubed minus t squared. Did anything convenient happen for us? Question? Yep, so, and again, this is not a coincidence this happens. I have told you this function is differentiable, so this limit better shake out in a way for us that makes it possible to get our hands around. So the t cubed and the negative t cubed are going to cancel out. And then from there, all the terms I have left in the numerator are going to have an h that gets canceled with the one denominator. So that leaves me with this limit, 3t squared plus 3th plus h cubed, not h squared. Is that limit possible to evaluate?
Yes.
What is it?
Zero.
No. It's 3t squared. Remember, so keep in mind what I'm taking to zero. It's not the t and the h, it's only the h. So yeah, the second and third term there are going to get annihilated, and I'll be left with 3t squared. So this right here is f prime of t. I don't want f prime of t. I want f triple prime. So now what do I have to do? F double prime. So f double prime of t. And how is that related to f prime?
First derivative.
It's the first derivative, right? So now I'm looking at this limit, f prime of t plus h minus f prime of t all over h. And I would rather do this. I don't think you need to watch me do this calculation over and over again. I'm going to say 6t, and I'm going to start next to this. I think it's worth practicing. Make sure you can actually do it, but I don't know if it's value added to watch me do it for 5 minutes. So the second derivative is 6t. Still not there. What do I need to do now? Okay, so the third derivative, how is that related to other stuff I have?
First derivative of f double prime.
Right. So now this limit is going to deal not with f prime or f, but f double prime. This one I will work out because it's pretty simple. So this is 6 times t plus h minus 6t all over h. The 6t's are going to cancel, right? And then after they cancel, the 6h divided by h is going to give you 6. So my third derivative ends up being a constant 6. Any questions there? Go ahead.
If f prime is a derivative of f of t, which is a tangent line, what does f triple prime look like on a graph?
That's, yeah, I was actually.
So that's a really good question, and we'll, in the last slide of this PowerPoint, we're gonna look at something like that, but if we're talking the languages of graphs and tangent lines, f prime, I remember one thing I want to point out is that tangent lines only exist at one point, right? So I can use f prime of t to find a tangent line at a point of my choosing on f, right? So if I graph f and f prime together, or sorry, if I graph f and that tangent line together, they'll make sense at one point. There is no like tangent line thing that makes sense if I compare f double prime and f, for example. But can I do something with f double prime? Tell me tangent lines about something else?
Yeah, about f prime.
The prime, yeah, because they're linked to this this first derivative idea, right?
Okay.
So let's think again about what a first derivative means. You know, we've talked about a lot of ways that a lot of things that a derivative is, and one of those things is a a derivative is an instantaneous rate of change of a function, right? Of whatever the parent function is. But when you start getting into these higher order derivatives, like, let's say I want to know about the instantaneous rate of change of f triple prime. I'd have to find a new thing called f quadruple prime. And if I wanted to, I could use f quadruple prime to find me the slopes of tangent lines on f triple prime. But when you're talking about instantaneous rate of change of a function, that's really only like one layer of differentiation. Okay. I'm going to say this is going to sound weird, but it's very much on purpose. If I want to relate f triple prime to f triple prime tells me the instantaneous rate of change of the instantaneous rate of change of the instantaneous rate of change of f. So, and that's not really mathematically why, but kind of symbolically why you can't take a third derivative directly. Because these rates of change only have something to do with the function that directly preceded them.
So these are still all straight lines, right?
Well, so remember, a tangent line, so t cubed, if you were to graph t cubed, it kind of looks like, that's kind of like the S-shaped curve. T squared, or 3t squared does not look good, that's gravity. And that's why I said it at the beginning, when you're talking about tangent lines, when you're dealing with a tangent line, you have to choose a point on your function. Because almost all the time, you're not talking about things that are linear, you're talking about, you know, that's a curve. This is a curve. This is a straight line. So this is a straight line, right? What's the slope of any tangent line to this straight line?
It would be the same.
It'd be 6, right?
Yeah.
What's the derivative of this?
6.
Yeah, not equal. So the derivative of any straight line will be a constant because you try to draw a tangent line to a straight line, you're always going to get the same slope, right? And kind of looking forward to our next lesson. This is a horizontal line, right? What would the slope of any tangent line be to this horizontal line? 0, right? So because of that, we'll learn why on Monday, but the derivative of any constant is 0. Because what's the instantaneous rate of change of a constant? If it changed, I wouldn't call it a constant, right? So the derivative of any constant for that reason is 0. Right, I got one more thing I want to do with you on this section, but I think it's a little too important to rush in a minute and a half. So I'm going to save this for Monday. Just a reminder, I actually don't think I've said this. I've told you the test is on Wednesday. It covers sections 1.3, whatever the one we started with was, all the way through 2.2. So we're almost there. In the first 10 minutes or so of Monday, we'll be through the test material. And again, I'm having a Zoom review on Tuesday night. I think I said 7 to 8:30 or something like that. Whatever, it's in the announcement. But yeah, please come to that if you need it. If you need anything else, email me. But yeah, it's coming up soon. So whatever you gotta do to be ready, just let me know. Otherwise, have a good weekend.